Hello, Catherine.
Hello, Catherine. Okay, so here's the next. We have two really big units left. One is on what's called kinetics, and the other one is thermodynamics. And they're somewhat related. But basically, this unit on kinetics boils down to the rate at which reactions take place. Now, some reactions take place very rapidly, okay, and that's a good thing, okay? So if you look at like the combustion of gasoline, let's say you have a gasoline-powered car, which I'm guessing most of you do. Okay, wow. You ingest into the cylinder mixture of air and fuel, the spark plug fires off, it ignites that, boom, you start down the road, okay? That reaction takes place very rapidly. You all have seen hydrogen balloons blow up, okay? Boom, very rapid reaction. Some reactions take place slower, okay? Say, for example, since you were a child, probably up until maybe 3 or 4 years ago, you were growing, okay? Well, it isn't like you're born as a child and all of a sudden that reaction rate takes place very quickly and you wake up the next morning and you're 6'3". Oh, okay, well that takes place very quickly, okay? So growth, in terms of human beings, while you're growing takes place slowly, okay? And that's okay, all right? You don't want to literally go from being, oh, I'm a toddler to 6'3".
I can talk about it like that first.
Damn, that was really aggressive.
Stop talking about you're not 6'3".
Did I at any point
I
say
can just
the
leave,
word
Berg. It's fine.
Skippy?
It's fine. I just leave.
He's a little heated, guys. It's a sensitive subject.
What is?
It's like, we're
Oh.
describing Zach. Zach has grown like 6
Or hair growth. You got hair. You got
Oh,
good hair.
great save. Great save.
Okay. Yeah, it isn't like you get your hair cut and you wake up the next morning and it's like, you know, out here you have to get a haircut. Did I save that?
You're great save.
Okay, thanks. Appreciate it.
Cut my hair.
I didn't realize that was a sensitive issue.
Oh, yes.
Oh, yes.
Wow,
That was
It
intense.
is.
that's touchy.
That was intense. It was giving toddler energy.
I just like can't stop thinking of Hasbula right now.
I have a bad vibe there.
Like Hasbula, I don't know.
Okay.
Energy.
I was like 5'4" last year.
And how tall are you now?
We would
5'10".
we would make
Okay.
him cry all the time in like 5th grade.
That's
Really?
cap.
I remember like
In middle school, she's just lying.
because like, we all like apologized to you because
She's
we
just
had
lying. She's just lying.
Pick on Sam.
no, like all of us were.
Oh, well, if it's a group thing, then by all means.
Above 6.
She's just lying.
No,
now.
it's
This
fine.
is
Go
not
on.
true.
Come measure me. I gotta be grown.
It's like 5th grade. It's
I'm gonna
You're
get
lying
that
on my
growth
head.
spurt.
Okay.
He was.
I did.
It happened.
Okay. Now that we have that,
Sorry, Berg.
I had no thought a growth analogy was going to turn into a whole class discussion.
Yeah.
Wow.
I was getting flamed over here. I couldn't say
Yeah,
it.
that got out of control fast. Okay. Now, here's the other thing that's going to happen, is that you all are used to thinking of reactions going in only one direction. So, for example, you look at hydrogen combining with oxygen to produce water, okay? That reaction goes, boom, one direction, hydrogen and oxygen are going to combine to produce water. There is no equilibrium that's established, that's just only going to go in one direction. But what can happen is that you have reactions where you have an equilibrium established, where you have a forward rate of reaction and you have a reverse rate. So let me go back and show you a simple example of how that works. So bring yonder camera.
Okay. I was just, you know.
Okay, let's go.
Yeah, physics! What class? Christina. Or not Christina. Catherine. Mark did that. AS.
You trust me with beakers again?
Oh, I don't trust you with fingers.
Where's a good,
Right there is good.
oh, for real?
Yep. Okay, so let me know when you're ready.
Oh, I am totally ready.
Okay. All right. So this is going to represent like a forward and reverse reaction. So Aspen's got this big 1,000 milliliter beaker. Huh?
No, I'm being lied about today. Look at this.
Wow. Wait. Can I zoom in on it?
Can you do both?
Yeah?
Do both. No, at the same time. Oh.
That was really good.
Okay. Hey, everyone's good. We did it.
Oh my god, I need to watch this YouTube video.
That's not going to be on the AP chemistry test.
Hey, this video might get a lot of views.
Okay. So here's what's going to happen. So you can think of this as being like the reactant side and this being the product side. Okay, and you all are used to water flowing in only one direction, but what can happen is we're going to reverse this. So what's going to happen is I've got this beaker. He has this one. Okay, so you're going to put yours in, fill it up. Okay, and then I'm going to do the same thing with mine. Okay, now, then I'm going to pour mine into yours. You pour this one over there. Now, what's going to happen to the levels of the water? So keep going. So who's going to fill up faster?
Yours.
Why?
The bigger rates of change.
Yeah. Now, we'll keep going. So initially, mine dropped very rapidly. Okay? Or excuse me, mine filled up very rapidly, and his dropped. Now, if we keep going, eventually what's going to happen?
They'll become equal.
There's going to reach an equilibrium point. Okay? So initially, there was a big rate of change. So if you can think of this, hold on. If you can think of this in terms of like levels versus time, and time is going to be a critical factor in all of these discussions. So imagine that you have a graph, and here was time, and here was the elevations of the two containers. So initially, the two levels were about the same. So initially, mine, that volume went up very quickly. Aspen's went down very quickly. But eventually, what's going to happen to those levels over a function of time?
They're going to flatten out at some point.
They're going to level off. Okay? Now, if you look at the units, in this unit, in this situation, this would be like volume, maybe like in milliliters. Okay? And then we'll have time. So if you look at the units, change in y over change in x, you would have milliliters per unit of time. And so the slope of that line would represent the rate of which that changed. So when that line flattened out, we're not saying, this is going to be important, when these lines flatten out, we're not saying that the reaction has stopped. We're just saying that there's no change in volume per unit of time. Now, we're going to reverse it. Now, we're going to go back. Now, I'm going to start over here, and you're going to start back over there. Okay? So now, what's going to happen to the volumes?
They're going to rapidly shift.
They are going to very rapidly shift. Okay? And again, eventually, what's going to happen?
This is really
You're going to
quiet.
flatten out again. Okay? Now I can fill mine completely up, but now eventually there's going to reach a limit of how full he can make his. So the point being here is that when you change the conditions of the system, you change the rate. But eventually Mother Nature wants to reach a point of equilibrium because that's when Mother Nature is most stable. So here's the mindset that you have to have. You have to get out of this mindset, first of all, that reactions only go in one direction. They can go, you can have reverse reactions. And if you reach a point of equilibrium, when you reach an equilibrium, we're not saying the reaction stopped. All we're saying is that it's reached an equilibrium where the conditions are remaining stationary. Got that? Okay, back we go.
Well, we're being examples.
that I just gave you, okay? So if you want to write this down, great, it's up to you. But you're going to see there's certain factors that affect the rate of the chemical reaction. Probably the most important one is temperature, okay? So temperature, and we'll spend a lot more time talking about temperature when we get into thermodynamics, but the short version of temperature from a chemistry standpoint is that it's a measure of the kinetic energy of the particles in the system. So if you're at 80 degrees Celsius, that's like giving a room full of second graders a tremendous amount of Skittles, okay? And they have a tremendous amount of energy, and they're bouncing around over the place, okay? Versus a room full of kids at 2 degrees Celsius, barely above freezing, they're not going to move around as much. So if you look at the role of a refrigerator, okay, in terms of preserving food, basically the role of a refrigerator is to slow down the reaction rate that would allow that food to spoil, okay? That's what it does. Like you can have, food sitting out at room temperature on a hot summer day, and that's going to spoil very quickly, or you can have that same food in a refrigerator, and that food's going to last a lot longer, okay? So all the refrigerator does is just slow down the rate of the reaction. So and you'll see this on the lab that you're all going to do next week. So the temperature greatly affects the amount of kinetic energy, and that impacts the number of collisions. The more collisions that you have, the faster the reaction is going to take place. So you can also have concentration. So one visual that you can have in terms of like concentration is that imagine that you have particles that are like randomly moving around, and you can think of this, it's somewhat of a decent analogy, of a lock and key, okay? Now, so if this is going to work, imagine these are like randomly colliding, and that key has to collide just right with that lock to open that up. So obviously, if you only have one lock and one key randomly moving around, they're not going to collide very often. But if you have a higher concentration of locks and keys, then you're going to have a more likely set of collisions that are going to happen. So typically, the higher the concentration, the faster the reaction is going to take place. Now,
I like your key.
that's a horrible key. How about this?
I was like, I feel like you can make a key really easily, but you made it very difficult for yourself. Yeah, that one looks good.
Is that better?
Yeah.
Okay, all right.
Oh.
Ooh, the old skeleton key.
Can you resize the lock, please? Can you keep them in proportion?
Now, the other one is going to be
Okay.
surface area, okay?
Oh my
So,
Bio. I'm
you
just
okay?
coughing.
Okay.
No, biology.
So, surface area.
Oh.
So, the more finely ground up you have a substance, the more surface area that you have, basically, the more surface area of the lock that you were exposing, the quicker that reaction is going to take place. So, like if you want sugar to dissolve, if you just have one cube, put it in there, okay, hey, it's going to dissolve. But if you take that sugar and you grind it up into a powder and then put it in water, that's going to dissolve a lot faster. Now, the other one is what's known as a catalyst, and we'll talk about catalysts later. You all have actually dealt with catalysts before when we did the reaction with acrylic acid, and we added magnesium sulfide, or manganese 2 sulfide, and I said, hey, don't worry about it now, it's just a catalyst. So what catalysts do is they allow the reaction to take place at a faster rate, okay? And we'll talk about the role of that in terms of how things take place. So catalysts aren't part of the reaction, but they're just there. So when you look at how this plays out, we're actually going to start off with making sandwiches.
Again?
Yeah. But now we're going to apply it to rates, okay? So we're going to take 2 slices of bread plus 1 slice of cheese, and we're going to make sandwiches, okay? Now, this reaction has the capacity to go in the reverse direction as well. So what that would mean, imagine this. Like, I'm on one side of the table, and I'm gonna take the bread, and I'm gonna take 2 slices of bread and put a slice of cheese in between it, and I'm gonna make that sandwiches. And then I'm gonna pass them over to the other side, right? And I get this big stack of bread and this big stack of cheese. And I wanna make sandwiches, okay? Now, what's gonna happen is that I'm gonna have those sandwiches across the table to Ema, okay? Ema's job is to disassemble the sandwiches and then throw those back to me. So I'm on one side making sandwiches. I'm passing them over. Ema is taking the sandwiches, taking them apart, and putting them back over here, okay? Now, it's kind of like the analogy that we just had with Aspen and the beakers. So, if I have a very high concentration of the bread and the cheese, initially, I'm going to be able to make a lot of sandwiches, okay? And my level is going to drop, because I can remember to make a lot of sandwiches. Ema doesn't have any sandwiches, okay? So what's going to happen is that I'm going to overload her with sandwiches initially, but then she's going to get caught up, and she's going to start taking those sandwiches and giving them back to me. So at some point, we're going to reach an equilibrium where whatever that rate is that I can make them, okay, and send them over is the rate at which she's going to push them back. Now, let's say we're going to change the system, okay? Now, me and Gracie are going to be making sandwiches. So there are going to be 2 people making sandwiches. Only one Ema is going to be disassembling them, right? So now, that's going to reach a different dynamic because we have 2 people making sandwiches and only one person disassembling them. Now, Gracie says, oh man, Mr. Burkamp, this isn't fair. I'm going to go help Ema. So she goes around and she's okay, I'm going to go help Ema. So now we've changed the system again. So now we're going to reach a different equilibrium. So as you change the system, you reach a different equilibrium point. So let's look at, there's a couple of ways you can do this. So let's start off with the idea that I am going to give you this 5 slices of cheese. Consumption of
Not English.
the bread.
I like the.
That's a consumption.
Locking.
Okay?
I would use.
So imagine this. So Zach has his watch and he's timing. Say, boom, go Burkamp. And he's watching and he's got a stopwatch. And at the end of 1 minute, I've used up 5 slices of cheese. Okay? So if I use up 5 slices of cheese, what I want to know is how many slices of bread that's going to take to match that consumption of the cheese. Okay? Now, I'm going to show you a couple ways you can do this. First off, one of the things you'll see in this whole unit is that time is going to be a huge factor. Okay? Because unless you know what the time is, it doesn't make any sense. So one option is that you can do stoic. Okay? It's valid. You can do stoic. You can sit there and go, okay, I got 5 slices of cheese, right? Per 1 minute. Okay? That's what I've got. I got 5 slices of cheese per 1 minute. What I want to know is the rate at which I've got to go through bread. So if you come up here to basically the chemical formula, you can sit here and go, okay, hey, that's 1 slice of cheese for every 2 slices of bread. Okay, that's just that mole ratio. It's a 1 to 2. So the cheese is going to cancel out. and I get 10 slices of bread per minute. Okay? There you go. So all this is just a stoic thing. Okay? And some people like that. If you like doing stoic, hey, that's cool, right? Now, there's another way that you could write this. And again, this is a personal preference. This will make sense in just a second. So, and this is what I've got on the lecture notes. And this will make sense. Let me explain what this is. It was horrible. So here's the story. So what these are the coefficients from the balanced equation, okay? This is just a different way of expressing this, and I'll show you how this works. So these are whatever your reactants are. In this case, there's just two of them. And the reason there's a negative sign in front of them is because of the fact that this concentrations are decreasing because I'm making sandwiches, okay? So that's what that negative sign indicates. That's the only reason that that's there. Because I'm going to be making sandwiches, the concentration of my sandwiches is going to go up, okay? So that's why that's a positive value. Now, just like before, you have things in brackets, that's just going to be concentrations, okay? Now, when you're talking about concentrations, this will play out large later on, just like when we did KSB, we didn't talk about the concentration of the insoluble product because of the fact that, well, if you're making calcium oxide, calcium, so whatever it is, and it's insoluble, it doesn't make any sense to talk about the concentration of it because it's a solid at the bottom. So the same thing is going to happen when you look at this in terms of things that you can measure. So when you look at expressing chemical reactions in terms of these, you only talk about either concentrations, like for example, the concentration of your silver ions, the concentration of your hydroxide ions, something like that. The other way that you can express this is pressure, okay? So that pressure typically is something as a unit called atmospheres, okay? So you can talk about concentrations in molarity. You can talk about pressure. What we're going to deal with initially is just going to be the concentration side, okay? We'll deal with pressures later. But we're not going to talk about the concentrations of solid particles, mainly because you can't talk about that. So you can only express, when you're writing these concentrations, these expressions, only worry about the ions if you're in an aqueous solution, or if you're going to be talking about pressures where you have like nitrogen combining with hydrogen to produce ammonia. Okay, but don't write down the solid parts of it because that doesn't. You just can't measure it. So if you were to use this, so for example, for the bread, so there's a 2 in front of the bread. So you would say, okay, that's -1/2 times the change in concentration of the bread over time is going to equal, now in front of the cheese, there's just a coefficient of 1, so that's just going to be a negative value. In terms of the concentration, change in concentration of the cheese, which we said was 5 units, 5 slices per 1 minute, okay? So some people like this because it turns into an algebra problem and they don't have to do the stoic. So this is what I don't know. So if I want to get this change in concentration per unit of time, oh, I want to get this by itself. Oh, I multiply by 2. So To get this by itself, I'd multiply both sides by 2. Okay, so that would mean the change in the concentration of the bread over time would equal 10 per minute. And that's the same thing that we got when we did the stoic. So I don't care how you think through it. Pick one. Either do the stoic or use the coefficients. Makes me no difference. You're going to get the same answer each way. But if you were specifically asked to write an expression about the change per unit of time, and if you're specifically asked to write just the expression, this is the format that you want to use. Okay. So let's talk about what can happen. So let's say, for example, and there's a couple of different ways you can express this. So let's say this is time. And let's say this is the concentration of my bread, and the concentration of the cheese, and this would be the concentration of my sandwiches. Okay? So the other way that you can view this is a graph. You say, okay, at time 0, I've got a whole bunch of bread, I've got a big stack of bread, and I've got a slice of cheese. And I've got no sandwiches. Okay? So eventually what's going to happen is that the concentration of my bread and cheese is going to drop. Okay? Because I'm going to start using those up. I'm going to start using the bread, cheese, then slapping them together, throwing those over. What's going to happen to the concentration of the sandwiches? It's going to go up. Okay? Now at some point, these graphs are going to level off. Okay? So what that means, when those graphs level off, what I'm saying is that I'm going to be making sandwiches at a certain rate, certain value per unit of time. EMA is going to be taking those sandwiches and pushing them back to me. And that's going to reach a certain equilibrium. So when those lines level off, don't think the reaction has stopped. We've just reached a point of equilibrium. Okay, we're good. Now, if I change the situation, I say, hey, Gracie, come help me make sandwiches. Oh, great. Then we're going to establish new equilibrium. Okay? So if you change the system, we're going to reach a new equilibrium. But you're still going to reach a point of equilibrium as long as the reaction can go forwards and backwards. Okay. Now, how you express this. Oddly enough, we're going to be talking about Q, and we're talking about Q. Okay, just like we talked about KSP and QSP, it's the exact same idea. So, anytime you use the uppercase K, what units are you referring to? Or what's the situation when you use uppercase K?
Equilibrium.
Equilibrium. Q is a snapshot, and that's going to tell you what's going to happen in terms of equilibrium. So, what could happen is that we start off and we say, okay, here's the concentration of the bread and the cheese. This is a function of time. So if you look at the units for this line, okay, and if it's a curved line, you could draw what we call a tangent line. Okay, don't worry about it. Tangent lines allow you to find like an instantaneous rate. Here's the whole point. When you have a sloping line, this is going to be a change in concentration per unit of time, which is going to be a rate. So, you have to, especially when we get into kinetics, you have to pay attention to the units. If you don't pay attention to the units, this whole thing is going to be a train wreck, okay? You have to pay attention to the units. So one of the things that we're going to be dealing a lot with, oddly enough, is rates, okay? Oh, rates. So because this is going to be concentrations, when we're actually doing it like with a chemical process and just not sandwiches. So any rate, well, I'm just saying, is because of the fact that it's concentration per unit of time, typically that's molarity per second. Sometimes you'll see it molarity per minute. If it's a really, really slow reaction, it's going to be molarity per hour. Okay, but 99% of the time, it's going to be molarity per second. So any rate is going to be in molarity per second. Now, there's different ways that you can express this. I'm going to show you three options. I don't care which one you pick. Okay? Now, what's another way of expressing molarity? So you could also see this written as moles per liter seconds. Okay? So that's an option. Okay? Okay, that's kind of cool. Now, if you're into exponents, you could also write it as moles, liters to the -1, seconds to the -1. I'm not, don't judge, okay?
Too late.
I'm just telling you. So these are your options that you can have in terms of how you express rate functions. I don't care which one that you do. Pick one, okay? But what you cannot do is say, oh, the rate is 1.2. I have no idea what that means. I don't know if that's micromoles per hour, molarity per second, kilomolarity per year. I got nothing, okay? So I don't care how you do it, just pick one. Now, if you go back to the cheese thing and the cheese sandwiches. So we had 2 slices of bread plus 1 slice of cheese equals sandwiches. Now the beauty of this is that we're going to follow the same format back we did before. It's products over reactants. It's the exact same format. So if you're asked to write the equilibrium expression, first off, you're only going to deal with the ions or the gases that you can measure the pressure on. So in this situation, it's going to be products over reactants. So I'm going to have the concentration of the sandwiches, because it's always products over reactants. Then I'm going to divide that by the concentration of the bread. But what am I going to do with the bread? There's a 2 in front of that, so that's going to get squared. And then I'm going to multiply that by the concentration of the cheese. So if we know somebody walks in and they're observing what's happening, and we've reached a point of equilibrium, okay? So these are going to be the concentrations, okay? These aren't the rates, okay? These are just the concentrations. So don't confuse rates with concentrations. Rates are based upon concentrations, but when you're dealing with your K values or your Q values, this is just what it is. So here's a simple example. So somebody walks in and says, okay, they make an observation that at equilibrium, the concentration of the sandwiches is 128. So that could be sandwiches like per box, okay? Something like that, all right? Here's a box. Oh, there's 128 sandwiches in there. And the concentration of the bread is going to be 4 slices per box. And the cheese is also 4 slices per box. Okay? So now, at this point, we can calculate K because we know what the numbers are. So we walked in, we've noticed that it's in equilibrium. Okay, the reactions are happening, but everything's staying static. Okay, we're not changing the concentrations of the sandwiches, we're not changing the concentration of the bread. Our concentration versus time graphs have leveled off. Okay, reactions are happening, it's just not changing. Okay, so in this situation, if I were to calculate this, I would take 128. And then I've got my slices of my bread, which is 4, but that's going to get squared. And then times the slices of the cheese, which is 4. And so you get 128 divided by 64, and you get 2. Now, K, just like we talked about before, K has no units. Okay? It has no units. Nothing. Okay? It's just a number. So this is one, a lot of times, and here's the odd part about this, is that I will preach to you, you have to pay attention to the units, you have to pay attention to units. But then on the other side, I'm going to go, hey, K, Q, they don't have any units, don't worry about it. Okay? They're just numbers, don't worry about it. So there's going to be times when I harp on you about units, and there's going to be other times like, nah, screw it, it's not worth it. And here's the reason why. It's hard to have the units of K, mainly because K can mathematically take on so many different forms. It might be a squared over a cubed, or it might be just one product over one reactant. And so there isn't like a standard format for K, and so that's why we just say, oh, screw it. Okay, whatever. That's why we just don't even worry about it, because it doesn't make any sense. Rates have units. Ks don't. So that's just a number. It has no units, it's just a number, 2.0. You plug in the numbers, that's going to get a value. That might change. So let's say, for example, the room cools down, and we're reaching a new equilibrium. Hey, if the room cools down and those rates change, that K value might be 5. It might be 0.3, okay? So don't look at this to go, oh, every K value in the world is going to be 2, okay? This is not a universal K value, okay? Just like when you look at Ka for acid, oh, there's a huge discrepancy. It might go 10 to the negative 4th up to 10 to the negative 19th, okay? KSP values might go from 10 to the negative 5th up to 10 to the negative 40th, okay? But it's the same idea, right? So this is why Ks have no units, because there's so many different ways that it can happen. Now, we're going to change the situation. So we're going to change this thing. We're going to flip things out. So I'm going to say that the concentration of the sandwiches is 100. Okay? So we're going to change the system. I'm going to take 8 sandwiches out of the box. And Ema's going to go, really? I took away 8 sandwiches. But I'm going to mess with the bread and cheese as well. So the concentration of the bread is going to drop to 2, and the concentration of the sandwiches is going to drop to 1. Okay? So I've taken sandwiches, I've taken bread, I've taken cheese. Okay? So now, we don't know if we're in equilibrium. Okay? So we've changed the system. Now we go, ooh, what's Mother Nature going to do? Because I've messed with Mother Nature. But now we're going to put the ball in Mother Nature's court. It's like, wow, what's Mother Nature going to do? Let's see. So now we're going to calculate Q. Okay? K only exists in equilibrium. Q is a comparison to K. Just like, remember, if QSP was a lot bigger than KSP, oh, you made a precipitate. If Q equals K, the system's in equilibrium. If Q is less than K, you don't get a precipitate. Okay? It's going to be the same idea here. So now, if I put these in, and now I'm going to calculate Q. So it's the same deal. I'm going to have the concentration of my sandwiches, which is 100. I got the concentration of my bread, which is 2, but that's still going to get squared, times the concentration of my cheese. I plug all these numbers, I get 25. Okay? I got 25. Now, my K value was 2. My Q value is 25. Okay? Q value is 25. Mother Nature is going to flip out. Okay? Because Mother Nature wants to go back to being in equilibrium. Okay? Mother Nature wants to go back. This is too big. Okay? It's too big. We need to drop this down to 2. So mathematically, how can I go from 25 down to 2 to get it back at equilibrium? What has to happen to the concentration of my sandwiches?
I'll divide it by 12.5.
Or not the actual numbers. Okay? So, what has to happen to the concentration of my sandwiches? Goes up, goes down.
Goes down.
So I'm going to decrease the concentration of my sandwiches. Okay? So Ema is going to have to work harder. Okay? So she's going to start disassembling this, like Mother Nature, like got a hold of Ema and said, hey, Mother Nature has flipped out. Okay? All is not well and right with the world. We got to get back in equilibrium. So I'm going to count on Ema to make take those sandwiches and disassemble them at a big rate, because I need to drop this concentration. But as she does that, what's going to happen to the concentration of the sandwich, of the bread and the cheese? It's going to go up. So what's going to happen, because my Q is bigger than the K, I'm going to favor, there's a random, favor the reverse reaction. Okay? Because Q is too big. So I've got to decrease the concentration of my products and increase the concentration of my reactants. Now, if the opposite happened, if I calculated Q and I got 0.25, so if Q is less than K, then what's going to happen? I got to make more. Got to make more sandwiches to decrease the concentration of bread and cheese. Okay? So that's the analogy. So now, if we do this, and let's say we got a value of 2. We calculate Q, and we get a value of 2 exactly. What would happen? It's just an equilibrium. Okay? We don't have to do anything because my Q equals my K. So you can have 3 options. Q is greater than K, Q is less than K, Q is equal to K. Okay? It all depends upon what Mother Nature is going to do to get that back in equilibrium. So, let's go with a real-life application.
I think decided that anytime I see reaction, I'm just going to pretend it's bread, cheese, and a sandwich.
Huh?
Do you like mayo? You seem like you would
Versus-
like mayo.
I do.
Yeah?
Yeah.
Okay. Who likes mayo here? Raise your hand.
I'm a mayo and ranch guy. It has to be like a little bit.
Wow, interesting.
Now, are you talking mayo or mayonnaise?
Aren't they the same?
No.
What?
Same.
Is mayonnaise?
How are they
Or Miracle Whip. I'm sorry. Miracle Whip.
Okay, no, not Miracle Whip. Mayo, like mayonnaise.
I'm sorry. I was thinking
What's
Miracle Whip.
Miracle Whip?
Miracle Whip is like, I don't know, my dad likes it. Like,
Is it like mayo?
It's like the trashy version. No.
mayo for 4 people.
It's like the Walmart version of Target.
Hey, don't talk about my dad like that.
It's like a Walmart version of mayo. Like, let's be so for real. Okay.
That's what we're marinara sauce.
No.
Those are not comparable.
Those are both made up to
No, that is so not comparable.
Okay, but what would you think if someone used mayo as like their dipping sauce?
Well, I prefer
Because like that's what
sucks.
Germans do, isn't it?
That's sour liquid.
No, like I heard like in like certain countries they use mayonnaise like as like a dip.
Would you rather put
That sounds disgusting.
I want to do it, but I don't know. Like straight mayo.
Okay,
Like that's straight mayo.
so here's kind of a simple.
God, I need to like wake up. I can't like. I'm
Okay.
not falling asleep in here.
So this reaction used to be very, very much more relevant than it is today. So, the ozone is an important part of our atmosphere. And ozone is actually, it's O3, okay? 3 oxygen molecules hooked together. And ozone can decompose into normal oxygen gas. So the reason that they used to be much more pertinent is because what we noticed, this is maybe 20, 30 years ago, is that we're getting these massive holes in the ozone over the poles, okay? And you think, well, who cares? Well, the problem why that is so important is because ozone is very, very effective at blocking UV light from the sun. And so the concern was that if these ozone holes continue to grow, then we're going to let in UV light. UV light has much more energy than normal visible light. It's going to cause more skin cancer. It's going to cause more distortions of your DNA. Bad things are going to happen. So what they figured out is that what's causing this destruction of the ozone was a certain class of chemicals called CFCs, that they were primarily used in Freon when you use Freon to make your refrigerants work. So they banned, and also they used them in aerosols, like if you wanted like hairspray or something like that. And so they banned this particular class of chemicals. And as soon as they did that, then they noticed that the ozone holes were there, but they were shrinking. Okay? And so it's like, okay, hey, that was a win for chemistry. Yay, chemistry. So here's what you can do, and here's the other side of how this plays out. Is that typically you can only measure one thing. So like in the lab that you're going to do, you're going to talk about the rate of disappearance of iodine, because iodine has a very distinctive color. Okay? So you don't have to know everything that's involved, but if you can measure one thing, then you can use that to figure out everything else. So let's say that we measure this and we notice that ozone is appearing at 6.00 times 10 to the negative fifth molarity per second. That is not moles per second. Okay, listen to me. That is not moles per second. That is molarity per second. And so if this is the rate at which oxygen is appearing, I want to figure out, well, how much ozone is disappearing to allow the oxygen to form. Okay? So you could have oxygen sensors, but we don't have ozone sensors. Oh, oxygen sensors. So if I can measure my oxygen, then I can work backwards and figure out what the ozone is. Now, so here's how you can do this. You can do the stoic part of this thing. You can go, okay. So if you look at this and go, okay, that's 6.00 times 10 to the negative fifth molarity per second. And this is of your oxygen. So then you can do the stoic and go, oh, okay, there's a 3 in front of the oxygen, so there's 3 moles of oxygen to every 2 moles of ozone. Okay, that's just a ratio. So if you do this, and oddly enough, that becomes 2, and you get 4.00 times 10 to the negative fifth molarity per second, which is the change in the concentration of your O3. Okay? So if you like stoic, all right, just do the stoic. Go to your balanced equation. Oh, there's a 2, there's a 3, boom, there you go. Now, if you're into algebra, okay, here's your other option. So if you were to look at these rates, so there's a 2 in front of the O3. So you have negative 1 over 2, which is the change in the concentration of your O3 over time. And then that equals, because of the fact that you're going to be forming oxygen, so you can write that as 1 over 2, 1 over 3. That's a horrible 3. Times the change in concentration of your oxygen per unit of time, which is 1 over 3 times 6.00 times 10 to the negative fifth molarity per second. So then it just turns into an algebra problem. This is what you want to isolate, okay? Because you know the rate of appearance of your oxygen, so you're just trying to get this by itself. So it's the exact same idea. So you're going to get this by itself, so you're going to multiply both sides by 2. Okay? So this is going to become 2/3. So when you do that, oddly enough, it's the same thing that you do up there. Oh, it's 2 divided, you're multiplying by 2/3. So if you're technically asked to write the expression that compares the rates, do this. That's the only way you can do that. If you're asked to write the expression, this is the only thing that you can do. But then, the beauty of this is then when you want to get this by itself, you're going to multiply by 2, and then you're going to still get the exact same answer of 4.0 times 10 to the negative fifth. Okay, so you can either, how you solve it, you can do stoic or you can write it out. But if you're actually asked to write out the expression, you have to write out those with those variables. Okay, I think that's it. Okay, we're in good shape. So this is out of your book.
That's an equation. That's what I thought.
Evan was sitting in this. Yeah. Evan was stepping on him a lot today. You first walked. On purpose or
On accident, because it's like 90 degrees.
I'd just be sitting there and then you'd go. First time I've ever won. Already doing 230. But Evan was playing footsie with me. Let's get it.
Stop.
What? My fault, Barry. I'm just a little emotionally unstable from what you said about me earlier today.
Did I ever explicitly say your name? No.
That makes it worse.
That's a big assignment.
You can stop writing Mr. Breaking.
I'm about done.
Actually, that's not even that bad.
But all these are like 4 parts each.
Oh, never mind. Yeah, good luck.
2 and 4.
No, it's
41.
Is that an A and E or A through?
A through E.
Oh, no.
You're just making it worse.
Not in Chem.
It's really showing right now.
Sorry.
Oh, those are biology terms.
Yeah, what are those doing? You said.
What are hatrogens?
The cross-referencing. What are we doing?
Imagine.
Imagine.
What?
Everyone's listening now.
Okay, so this is on your equation sheet. So
They'd have
what
to tell
this
their lives.
is, this is allows you to convert between a K value based upon concentrations, that's what that Kc stands for, versus Kp, which is a value based upon pressure. So I've got this on here. That R is the ideal gas law constant, and there's different versions of R. With this one, and I've got this on the lecture notes, you need to use 0.0821 liter atmospheres per mole Kelvin. Okay? This temperature has to be in Kelvin. And remember to convert, how do you convert from Celsius to Kelvin?
Plus or minus 270.
Yeah, you're going to add 273 to it. And pressure is going to be your normal atmospheric pressure. The delta N is the change in moles of gas. Okay? So you take the total moles of gaseous product and subtract that from the moles of gaseous reactant. The solids, the aqueous stuff, doesn't matter. It's all about the moles. So if delta N is 0, well, what's anything raised to the 0 power? 1. So if delta N is 0, this just has a value of 1. So just keep in mind with that. So there you go. And when this makes sense when you get to 15, you have to tell if it's a homogeneous or heterogeneous situation. Okay, so for example, like let's say for example, here's the classic example. You drop a piece of magnesium into a solution of hydrochloric acid, and you get magnesium chloride and hydrogen gas. Okay, so this is like the quintessential example of a heterogeneous situation.
I want to be an artist.
Because you have a solid dropping it into a solution which forms this another solid and then a gas. Okay? So that's like the classic example of something being a heterogeneous reaction. So, okay, I'm done. I know the Softies have to go.